Go ahead and start. Okay, so today we're going to talk about, we're trying to get through chapter 3. We might be able to do that today to finish it up. So, yeah, concepts like purification. This, Soria actually already asked about it in the previous lecture. So we'll elaborate on that. And then we'll start talking about quantum measurements. And we might be able to finish it. Okay, so state purification. So let rho A be the state system A. And a purification. The name's a good name, but it is what it says. Purification of rho A is a pure state R. So psi R, right? So it's a state on a tensor product Hilbert space. And the main condition is that you take the partial trace over this reference, you get back the original state. Okay? So if you want to think of it in terms of a diagram, this is the kind of thing we would draw. This line would correspond to a state on system A. And then what we're doing is we're attaching this reference system, and the joint state is psi RA. So the usual thing we do is that this is an abbreviation. We get tired of writing psi twice, and so then we just write it once. Okay? So purification is a uniquely quantum phenomenon. This does not exist classically. And some people in their pursuit of understanding the foundations of quantum mechanics from like an information theoretic perspective, this was something that really separated. They elevated to the level of a postulate. It separated classical from quantum. But that's the topic of research, and we'll get into that in this course. Okay, so the way of thinking about this conceptually, and we'll return to this in a minute, is the state rho A can be a mixed state, right? The rank of the density matrix can be strictly larger than 1. And in that case, it has this interpretation that we've been talking about, that in the background, someone could be preparing a probabilistic mixture of more than one possible state, and then that's the reason it looks mixed. This gives a different interpretation of mixedness. The interpretation here is that the mixedness of the state, or the noise in the state that makes it probabilistic, is due to entanglement with a reference system that's inaccessible. Okay, so that's an alternative way to think about it. Let's write that down because it's very important conceptually. Mixedness can be thought of as being due to entanglement with an inaccessible reference system. We could just say an inaccessible system, but it's traditional to call this the reference system. Okay, so how to construct a purification? Let's do that now. It's a theorem. It's a simple theorem. Every state rho A exists a purification such that the dimension of the reference system is larger than the rank of the row. Okay, so what is the proof? It's a nice and simple proof. you take the spectral, you take a spectral decomposition row of its and then it's like you could actually just flip this raw to a ket, and that would work. Okay. Oh, then you need to take square roots. So it's more. So let's just try it. So construct the state vector psi array like this. Convert the probabilities to probability amplitudes. Remember, these are real and non-negative. We just take the square root, and then we can pick an orthonormal basis for the reference system. K, and then put phi k. Right? And that'll do the job. So we can do that calculation real quick. And we have to just check this one condition. Right? So let's just do it fast. So we need a double index, x and x prime. Oh wait, I have a mistake here. I'm sorry. I'm looking at my notes and talking. The sum should be over k. Right? Sum should be over k. So do k and k prime. K. This is the density matrix. And then we need to trace. We need to trace over the reference system. So I'll just, the trace is linear. I'll just bring it in right here, slip it in, trace. Right. So what happens when you do that? This collapses to delta function, and then that's it. This collapses to a scalar. The tensor product of the scalar is like the usual product. And then you're left with precisely this. Okay. So what happened in this process? We changed probabilities to probability amplitudes. And we introduced this orthonormal basis here. We could have equally well used phi k as the orthonormal basis. You know, some people think of this as like a kind of mirroring process where we mirror these states right here, and then we do it coherently in superposition. Okay. Good. So you see right here in this proof, I mean, that's the end of the proof. You see right here in this proof, we could have chosen the orthonormal basis to be any orthonormal basis. And this would have worked. Okay? So, you know, the statement we can make now is, let's call this like a corollary. The psi RA is a purification rho A, and so is. So now I'm going to use this notation where I'm suppressing identity operators. Okay. Where V going from R to R prime, psi R A, V R to R prime. Okay. Where V is an isometry. Okay. So going back to this diagram, I want you to think of this state in terms of this kind of quantum circuit diagram, like this. This right here is the pure state psi array. We can act on the inaccessible reference system. You can imagine that someone's there and they apply an isometry. Okay? An isometry is a generalization of the unitary evolution, and someone could physically apply that to the reference system. Okay? It's a kind of quantum channel, so it's a legitimate physical evolution. They would apply V, and the output would be R prime. Right? If you want a very specific example of an isometry, so suppose that actually we talked about superdense coding, right? We talked about superdense coding, so we can use that as an example. We can have the maximum entangled qubit state 5 plus, right? And in superdense coding, the isometry applied could be a unitary, right? So that was one of the Pauli algorithms. You can apply X, and then this state would be psi plus. Right? And so psi plus and phi plus are both legitimate purifications of the reduced state here. What's the reduced state here? A maximally mixed state. Okay. What is another example? It's more like an isometry, not be captured just by the unitary. So it could be that the reference attaches, we often call it ancilla qubit in state 0. And then you can do a controlled knot. Controlled knot is a gate from quantum computing. I believe we have not talked about it yet. I believe many of you know what it is. We'll just write it. So the controlled knot is this on basis states. And that's its action on basis states. And then for arbitrary superposition state vectors, it acts, you extend this by linearity. Right? So if you do this, this is an isometry. The action of censoring in a pure state and performing a unitary, that's an isometry. Okay? That's what you can show. What is the state that you get here? The state vector is something we call the GHZ state. That's a kind of example of this. And then, the first 2 qubits would be with the reference. These here would be. These are with the reference, and this is the ballast. These are with the references. So you can see if you do the calculation in this case, if you trace over both reference qubits, you're left with maximum state. That's another purification. So why is this true mathematically? Well, and you notice one thing I'll point out with the notation. This means that the output system R prime can be different from the input system R. That's what that notation means. So in this example, R is a single qubit, but R prime, actually to be precise, I should have, in this notation, I should put primes. So the notation indicates that the input and output systems of the isometry can be different. Here we go from 1 qubit to 2 qubits, different public spaces. So why is this true? Well, we need to check the trace of VR R prime. Sorry. Trace over the reference system. So what property can we use? This V is acting only on the reference system. Okay, so the usual trace, you have a cyclicity property. Okay, for partial trace, you have that if the operator in question is acting only on the system that you're tracing over. then you can use, there's a simplicity of partial trace. I don't know if we explicitly wrote that in the book, but it exists. And the proof is the same as the simplicity of trace. Okay? So what does this allow us to do? Well, that, right? Write it down. ER, R prime, vector, psi, R, trace over R. And now what? Now what can we do? We said it's an isometry, so what is this equal to? This goes back to our math lecture with like the million facts that were spat out. Yeah.
Why do you have the trace with respect to R and not R?
R prime, thank you. Yes. Oh, but now it's on. Yeah. Yeah, thank you. All right, so what property of isometries can we use? The defining property of an isometry. That's right. This right here is equal to the identity on the reference system. So then it's R, psi RA, and then by definition, psi RA, by hypothesis, psi RA is a purification of rho. So then that shows that this claim is true. That's the end of the proof. Okay. So yeah, that's about all. There's one other statement to make about purification. We're gonna move on. Any other questions about this concept? Why is it distinct from classical? It's what we said the last time, right? Classically, it's impossible to have a definite joint state, a mixed reduced state. You can't have it. If you have a definite state, if you have a definite joint state classically, then the reduced state is definite. That's a big distinction. And then you see underlying that are two like uniquely quantum principles, superposition and entanglement. Right? Okay, so next statement I want to make is this was a corollary. It has an if part. It actually has an only if part as well. Right? So only if part is that two states, two pure states, psi RA and psi R prime A. We'll put a prime on the psi also. Okay, so the reference system can be different. The two pure states purify the same state rho A if and only if there exists an isometry such that, now working with the state vectors, it's called the isometry, again, this BR to R prime. We're assuming that R prime is the larger of the systems. And then precisely this kind of equation, I'll just write it with the state vectors. Okay, so this is quite strong. A short and nifty way to summarize this is like a slogan. Is all purifications are related by ensemble. So that's an important concept. This is the first manifestation of this concept that we'll see. We'll see something similar for quantum measurements, and we'll see something similar for quantum channels. Okay. There will be ways to purify quantum measurements, and there will be ways to purify quantum channels. Okay, and so what's pleasing about that is that, you know, in quantum information, we're saying, oh, you have to use density operators, you have to use POVMs, you have to use channels. But guess what? With purification, we can go back to the way that you learned quantum mechanics undergrad. We can use state vectors, we can use unitary evolution, and we can use von Neumann projective measurements. And that the whole theory can be captured that way. It's like you start out and you say, oh, we need this for jumping, and you go back, and like, actually that suffices. As long as you purify the larger spaces that we don't have access to. Okay, so that's an important concept of this course. So we proved one way of this theorem. We proved that if there exists an isometry such as this is true, then they both are purifications of the same state. The other part of this is to show that only if, I guess. And for that, you can use Schmidt compensation. We won't get into that today. But the basic idea is that you start out with this fact that they purify, then the reduced state of both psi r a and psi prime. I mean, I'm just going to explain the proof right now, actually. So you start out with the fact that the reduced state is the same, so the reduced state of this can be written like this. Then from Schmidt decomposition, you know you'll be able to expand like this for purification, and you know that the reduced this basis here has to be the same as the basis from the spectral decomposition. And there will be some basis here. So that's what you do for psi prime. You have something similar, but a different orthonormal basis here. And then what relates to orthonormal bases is an isometry. So that's the basic idea. So let's just leave it at that. All right. One final point is that there's an interesting way to construct like the canonical purification. Remember the maximum entangled vector, the way we define it, we'll redefine it over here, is like this. You can take the maximum entangled vector. Remember we talked about functions of Hermitian operators. Function that you can apply to a Hermitian density operator is the square root of rho A. Censor that with identity on the R. And then this is a canonical purification of rho A. And so conceptually what you see going on is something like what we were saying earlier. There's a superposed state, and then you're taking probabilities to probability amplitudes. Right? So the square root of a density operator, what does that look like? Well, this is what happens. Right? So it's like in this process, you change the probabilities to probability amplitudes. You made a superposition. So to prove that this is a purification, let's just talk about it. Now I'm going to use a notation where we'll suppress the identity. So the partial trace is over the reference system, but this doesn't act on the reference system. If you want a diagram, we can think of it like this. Here's gamma. And this is like a box corresponding to rho A. So what are we doing? We're tracing over the reference system. So that'll use the trace symbol. And then the point is that the trace and this operator commute because they're acting on different systems. So this can go past this box here, the trace of the of this operator here over the reference system is the identity on system A. So that's an argument that, well, do the trace over the reference, it commutes. Why don't we write the math of the commute? Clear. And then what I was saying is that you can do a quick check. This is identity on system A. And so you got row A, identity of A, square root of row A, and then forward slash just row A. So that's the proof of the canonical purification. All right. Okay, there's another concept. This will be very short. It's just we want to say the word extension of a state. Extension of a state. So omega RA is an extension if we trace over the reference system of omega, you get back rho. Right? So it's less stringent than a purification. The extension is not required to be a pure state. And so this you have in classical probability, classical information. Okay. The reference system can be arbitrarily large, right? Okay. And then you can connect this to purification as well, right? So like I could do something. This might even be like a homework exercise. I don't know. So you could say, okay, let I R prime RA purify omega RA. Then you could say, oh, well then I R prime RA purifies rho. Right? The purification here of rho A is fire rate, but now this terminology, I don't know if we probably said it, but R prime and R are the purifying systems in this case. These are the I realize now there's one other point I forgot regarding purification. So suppose rho A, our discussion was kind of exclusive about the case where rho A was a mixed state with rank 2 or greater. Right? But now suppose rho A is a pure state. Then the question arises, well, like, how do you purify a pure state? It's already pure, right? How more pure can it be? So you can show that the only purification of rho A has the form tensor product. R. Okay. A subtle point is that we said in the theorem about constructing purification, the dimension of the reference system, it only needs to be greater than or equal to the rank of rho. In this case, the rank of rho is 1. And so the reference system R could be a one-dimensional system. What is a one-dimensional system? It's like a trivial system. And so it's like, you know, the trivial system is like you're multiplying with the number 1, right? And so it's like, to address this question that we said, how can it be more pure than it already is? Well, it's already a purification of itself, technically. Okay. So it's maybe kind of weird to think about. But of course, you could put an arbitrary pure state of a reference system of dimension 2 or greater, and it's still a legitimate purification.
What about mixed state?
The definition of purification is it has to be a pure state overall. So if you put a mixed state there, it would not be a legitimate purification. Then you can question whether the number 1 is a pure state or a mixed state. It's both. It's like kind of a silly question. But it's, you know. So, okay. Anyway, that was some point to make. All right. And indeed, like, okay, so maybe we should come to what you were saying in some way. You could ask about an extension of a pure state. Right? So an extension, you could put any mixed state here, and that's fine. Right? That would be the definition of extension. But there is a point to make that the only possible extension of a pure state is one where you have the original state and a tensor product with some other state. This is the basic principle behind quantum cryptography, behind schemes for entanglement-based quantum cryptography. So this is an important conceptual point. I don't know if it's really, but actually it is in the chapter on private communication. So suppose that this is a state of Alice and Bob, right? And like somehow it's impossible to do it, but suppose you get very close in the lab, in distant labs, to producing an entangled state of the system's Alice and Bob. Right? So like there's Alice's laboratory, it's physically secure, and everything else, there's Bob's laboratory, it's physically secure. In there, they produce this, somehow managed to produce this fire that's in a pure state. But guess what? Anyone outside the labs, eavesdropper, their state, the overall state, because of what we're saying, can only have this form, a tensor product. So the eavesdropper, we often call it Eve, the eavesdropper system is completely independent of Alice and Bob's systems. Right? So whatever measurements they do, Alice and Bob can do local measurements. The measurement results are guaranteed to be independent of Eve, and all she can do is try to guess what they were. They try to randomly guess what the outcomes of the measurements. That's the basic principle behind entanglement-based quantum cryptography. So that's how this purification connects to something quite practical. You know, quantum key distribution is much closer. I mean, there are systems in existence. You can question the security, but it's much closer to being truly implemented than a quantum computer. Okay. I want to talk about another concept related to symmetry. That's group invariant states. Often we'll be looking at channels. You know, one of the stated goals of the class is to calculate capacities. Right? And there'll be channels of interest that we'll look at. We'll start talking about the phasing channels, the polarizing channels, erasure channels, loss channels, etc. Many of these channels have natural symmetries. Okay? With natural symmetries, certain unitary operations will commute with the action of the channel. And then we'll be interested in optimizing information functions of those channels. Calculate capacity which corresponds to data. So if you're faced with an optimization problem, and you know there's symmetry there, you had better use it because it'll make your life simpler. Like reducing the search space, you might cut it in half or cut it in a quarter, depending on the amount of symmetry you have. So that's where this concept comes up in the context of this class. It's also just a general aspect of physics, that symmetry is a concept. Okay, so let's, it might be a reminder, it might be new. We'll briefly talk about what is a group. A group is a tuple. I'm going to use the same notation for the group and the tuple. I hope it's not following. In the book, there's a distinct notation. So it consists of set G and an associative operation. Star. And star, this is the multiplication operation, defined so that G times G prime is in the group if G and G prime are. Okay. There exists an identity. Call it ID. Satisfying we could expect. The identity multiplies G, you get back G. And there's an inverse associated with every group element is inverse. Denote with expected notation. G times G inverse equals identity. That's the basics of a group. And then relevant for us is that there are unitary representations of the group elements. And unitaries have action on states, right? They evolve states. So the symmetry is that like state does not evolve under the action of unitary. It stays stable. Symmetric with respect to the action of the group, of the representation. All right, so a unitary representation of G set UG, G is a label. Unitary operators. They have this it's called homomorphism problem. So UG times prime equals. If you multiply the unitaries, it's the same as finding the unitary that corresponds to the multiplication of the group elements. Okay? Then you can figure out things that like, well, unitary corresponding to G inverse has to be UG dagger. And then the identity unitary corresponds to the group identity element has to be the identity operator. Okay. So the action of the representation of the state is this. The rho goes to UG rho. Good old unitary evolution. And this is chronology. So coming back to the key words said here, group invariant states. State is group invariant. State row is group invariant. Row equals, it's unchanged in the action of the unitary representation. This has to be true for all G. And there's an interesting homework exercise that, if you apply a channel called the twirl channel, what is the twirl channel? It's that you randomly apply a group element to the state. Okay? So this is called twirl channel. If you think of, I won't give you a demonstration, but the idea is that you think of a unitary like a rotation. If you do a random rotation, it's like you're twirling around and randomly pulling some spot. Okay? So that's the twirl channel. What is the point I wanted to make here? If you have a state that's not symmetric, satisfying this, or group invariant, then you can apply a random twirl, and it will be. It will then satisfy this condition. So after twirl, state comes group invariant. In this class, you can think of the twirl as like a loss of information. Maybe you had some quantum information encoded in a state, did a twirl, and then it somehow lost in the mind. So let's talk about,
Discrete finite groups, right?
this is finite. Yeah, we're not going to do this. You do have a notion with a compact group.
Yes,
Compact.
you have the hard measure.
Yes.
Or compact groups.
It need not be a billion. Yeah. Good. All right, so let's talk about some examples. These are just very basic examples. In the book, there are more elaborate examples involving the symmetric group. So some examples. Look at the literature. It's been kind of a popular topic in quantum information to talk about resource theories. Like we'll learn that entanglement is a resource theory. We already saw that if you have entanglement, you can do synchronous coding. So it's a resource for information. People have also thought of coherence as a resource as well, quantum coherence. There's been many papers about that now. So what are incoherent states? Well, it's those that satisfy a certain symmetry with a choice of a group. So let's think of just qubits. Z this, Z2, represented by identity in sigma z. So this is just the qubits. So what are the group invariant states? It's going to be those that satisfy they're diagonal. But they're, the hint here was this incoherent. So the off diagonal elements are gone. So we have this form P0 1 minus 1. What do you think of as the probability between 0 and 1? So No off-diagonal terms. Off-diagonal terms correspond to what we call quantum coherence. Like when we talked about coherent superpositions, we saw the presence of off-diagonal terms. Right? So these group invariant states, the coherence is lost. Okay. What's another example? Permutation symmetry. Let's just talk about it for 2 qubits. So we're going to take the symmetric group S2 and we'll represent it by 2 qubit unitaries. Call them identity and swap. So what is swap? You can write it like this, where I and J are orthonormal bases. So like if this acts, suppose I have qubit A and qubit B here. If the swap acts, literally what's done is a physical swap. Okay. And that's actually quite an important unit set, even though it seems like simple. So I mean, what do you see happening here? Whatever comes into this system, maybe this is the A system, this is the B system. So whatever comes in on B goes to A, right? And whatever comes in on A goes to B. So this I will catch whatever's coming in on B and put it on A. And this J will catch whatever's coming on A and put it on B. And it does that. Technically, we've been drawing diagrams like that. But, so what's an example of a group invariant state? So 5 plus. Now you can check. And then other examples, and when you learn about spin representations in quantum mechanics, you learn about triplet subspace and singlet subspace. Right? So it's called triplet because there are 3 states that are invariant under swap. The others are psi plus and phi minus. You can check that these Bell states are invariant under swap. The +1 eigenvectors of swap. And then the singlet is, it catches a minus sign in their swap. So it's like the anti-symmetric state. Okay. So those are just some examples of group invariant states. And there are many others. We're going to move on to it. Okay. When we talked about density operators, we said like, oh, in the background, I could be probabilistically applying, selecting some letter, and then sending the state that I selected. So that's related to a concept called ensemble. And a related concept called classical quantum state. As far as I can tell, this concept of classical quantum state really only seems to appear, it's like started in quantum information. And then moves from there. What is an ensemble? It describes this process that we're talking about. It's a collection of pairs of a probability with an associated state. Some alphabet of what you're selecting is. Right? So, you know, you could think that as a probability 1/2, I pick 0 state, or probability 1/2, I pick 1. That's a simple example of ensemble. Okay, so we're clear. These are paired up with states. Okay, so suppose that we have a process like Alice is selecting from this ensemble, and then she sends the state to Bob. How would we describe the density operator of Bob? So Bob doesn't know which X was selected. Let's think about it in a different way. Suppose we, Alice sends this ensemble to Bob, doesn't tell which X was selected, and then we want to know how to predict the outcomes of measurements in Bob's system, because that's all that we can see, really, the outcome of measurements. Right, so suppose there's a POVM called MY. If you knew which state was selected, and we were talking about a conditional probability distribution. So suppose that you know which state was selected, that was revealed to you, and then you want to calculate what are the probabilities of getting certain outcomes. Well, conditional probability distribution, what would that be given by? Is that like a quiz for the Born rule? So we're doing a measurement described by this POVM, and then there's a state rho X that's selected. We know for sure which is selected. So what's the probability of observing outcome Y, given that the state labeled by X was selected? Yes, good. Right, like that. Good. That's a conditional probability distribution. In classical problems, so we've identified this probability distribution, right? So then the joint distribution, this is, this basic probability theory. The joint distribution is this, right? But now, the original situation we're describing is that you don't know X. You don't have access to X. Then we're interested in the marginal distribution of the measurement. But to calculate that from probability theory, we use marginalization. Right? P of Y is this. When we marginalize, P of X, now let's plug in with the Born rule. So everything's nice and linear. Right? We can exchange trace and MY with the sum and probabilities. Now, right. So it's answer the original question. This is the density operator of Bob, who doesn't have access to X. So let's write this down. Using this ensemble. Let's label the ensemble. Let's call it E, or curly E. We're using ensemble E. And doesn't tell which X was selected. The statement we made is that the outcomes of measurements from Bob's systems in this scenario can be predicted from this operator. So that's Bob's density. That we'll just call rho for short. That's Bob's density. Okay, so I want to describe this situation in a similar way and use some, it's kind of like quantum circuit diagrams. This is the diagram that I want to use. This is Alice's lab. We could equivalently describe the scenario using the formalism of classical quantum states. So what's going on with this picture is that this is a classical system X that Alice has access to, maybe in her brain or whatever, where she remembers, which state was chosen. And A is the quantum system, in some physical system. The classical label could be in some physical, it's in some physical system as well. And the joint state at this point is what we call classical quantum state. The key point here is we pick an orthonormal basis, some known basis to Alice. So that's an equivalent way to describe the ensemble. Right? But this is from the perspective of someone who knows the choice of the classical letters. Right? So it's like randomly generated, but someone who knows the classical labels. So that's Alice. Then what happens? She sends A to Bob, and so we can describe the joint state at that point. Rho XB. I'm just going to write the whole thing down. And then that's the state at this point. This is rho X. This right here is rho. So this fully describes the scenario we were discussing. And at this point, all Alice has access to is the classical label. The quantum system is gone. We haven't talked about it yet, but there's no cloning theorem. So it's not like Alice could copy the quantum data here and retain a copy in her lab. That's impossible. Okay? It's impossible in general unless these states form an orthonormal basis, unless the states are classical themselves. Okay? Or unless they're more generally orthogonal to each other. Okay, so we use these words here. We could change the words to, if Alice prepares a classical system and a quantum system in this way, and now sends B to Bob, that means that he doesn't have access to this X. So how do we describe the state of Bob's reduced system? Partial trace. Okay, that's what we learned about before. So the state of Bob's reduced system trace over X, rho XB. Do that calculation. Trace is linear, sum over X, BX comes out. We get this. Trace over X. And then, you get the same thing that we wrote earlier. Okay, so the point here is that both pictures are equivalent. In many scenarios, it can be helpful as a calculational tool to use this formalism of classical quantum states. Okay, so now a question for y'all is a classical quantum state, or the state made here, is it a separable state or entangled state? I don't know if that's simple. So, definition of separable state is a state is a separable state if it's a convex combination of product states. We have that here. Yes. See a product state, convex combination. So, shorthand notation, often we just say CQ state for classical quantum. That's a shorthand state. So CQ state is a special kind of separable state. All right. Any questions about this? We're going to move on to a new concept. Okay, so the new concept is a way to test for entanglement, and it's probably the first test discovered, called partial transpose. Different from partial trace. Okay, so I believe that you know what transpose is from linear algebra. And I believe we reviewed that in our big math review. The transpose, ordinary transpose, its action on operator X. You can think of it as a superoperator. It is basis dependent. So if you want to take the transpose, you have to pick a basis. And what do we always do? We pick the standard basis. These are like Krauss operators of the transpose. We talked about quantum channels. The partial transpose is not a quantum channel. It is not completely possible. If it acts on one, okay, we'll get to that. We'll get to it. We'll talk about partial transpose. Okay, so partial transpose is an extension of this concept to bipartite operators. So we use a shorthand where we'll suppress identities. That's a common thing that we do. Suppress identities. And typo in the notes, TB of X. Talking about the action of transpose on one share of a bipartite operator. So what is that? Well, it's going to look like this in this first line, but we're going to tensor these operators with identity, maximum basis. Okay, that's how it's defined mathematically. And now we can start talking about what does this operation do to certain kinds of quantum states. That's where it's useful. We said we wanted to relate it to ensemble. Right, so keep in mind it's not a channel, so you cannot implement it precisely. People have tried to approximately implement it, and there's interesting things about that. But let's see what happens when the partial transpose acts in a separable state. Okay. This is the observation. Partial transpose acting in a separable state. We already remind ourselves that a separable state is a convex combination of product states. So we'll call the separable state sigma AB. This is what we're interested in. So sigma AB we can write as a convex combination of product states. Let's do that. Now we can use linearity. And then what is going on? Well, in this partial transpose, identity is acting on system A. So these tau xa's are unaffected. And then the TB will act on omega xb. But that TB is equivalent to an ordinary transpose. Like everything factors nicely with the separable state. So we can do that. T omega xb. This is the ordinary transpose. Okay. And what do we know about the ordinary? What is the relevance of the ordinary transpose to quantum information? So if the key fact about the ordinary transpose, if X is positive semi-definite, then T of X is positive semi-definite. That's the key observation. Okay. And so each of these is going to be positive semi-definite. Okay. By applying this fact. And then now let me ask you, if I take the partial transpose and act on a separable state, is the resulting operator positive semi-definite? Let's think about it. So these are positive semi-definite. These are positive semi-definite. The product of them, you can think about positive semi-definite in terms of the eigenvalues. Right? So that means that the eigenvalues of this are non-negative, eigenvalues are non-negative, or the eigenvalues of the tensor product, it's the multiplication of the individual eigenvalues. So each of these is positive semi-definite. Then we're taking a non-negative combination of those. So the resulting operator will be positive semi-definite. So we conclude that TB may be is positive semi-definite. We did this with a very special class of states, separable states. Okay? And what we'll get out from this is a one-sided test of entanglement. This gets used a lot. This is like in experimental papers. This is the most common test of entanglement. But there's ways to change this to measure entanglement. Like you can take the partial transpose state and compute the one norm. It turns out that's a measure of entanglement. Hopefully, we'll get to that in the entanglement chapter. Okay, so the key line that we can take from this is that state is separable, then it has a positive partial transpose. This term positive partial transpose, it also, we can abbreviate this as saying it gets turned into like an adjective somehow. I don't know. People say then it is PPT, right? That's another thing that people, you'll read in the literature. It becomes an adjective.
Is there a distinction between partial transpose and partial trace?
Yes.
Calling it P, well, I didn't just, but like, because you call them both like PT, so is that?
Oh, yeah, it's not common literature to use PT for partial transpose. That was just a tool for the class to go fast. Yeah, so, right, indeed, when you see PBT, this is what it means, and I'll try my best to avoid using PT for partial trace. Okay, so but the meaning of then it has a positive partial transpose is exactly this. Right? Okay. So, according to basic logic, if you have an if-then, if A then B, then the contrapositive is true. If not B, then not A. So the contrapositive is more interesting. If a state has a negative partial transpose, what is the opposite of separable? Entangled. Then it is entangled. Okay. So let's do the partial transpose for the case of interest, maximum entanglement. And then we'll see that it has a negative eigenvalue. So it's often called PPT test. Okay. So 5 plus PB, right as 1/2 IJ 1. Then if you apply the partial transpose, we do the partial transpose. We wrote it this way, but what it amounts to is just on the terms in this factor, they're the ordinary transpose. So we're at TB 5 plus this. Becomes that. Okay. What operator is that? That's one that we actually just wrote and erased a few minutes ago. Swap. Yeah, this is swap. This is 1/2 times swap. Right? And then we said that, we said that 5 plus, psi plus, 5 minus are plus 1 eigenvectors of swap. We said that psi minus is a -1. That means that swap has a diagonal representation in the Bell basis. If we written as 5 plus 5 minus 5 plus, then minus. And that's the negative argument. Minus 7. Negative argument. So, indeed, 5 plus has a negative partial transpose, and so therefore it's entangled. We already knew it, but this was an example. Right? We knew it for the Schmidt decomposition. This is more useful for mixed state entanglement, accessible mixed state. So let me emphasize this is a one-way test for entanglement. It does not identify all entangled states. But that is because there exist what are called PPT entangled states. That means that there are some states, tricky as they are, such that they're entangled, but when you do this test, you still get a positive partial transpose, and then we can't conclude anything from this. Okay. But in the sense of this class, the amount of entanglement in those states is essentially not very useful. They're not very strong. So, we'll ask questions like, okay, given many copies of a state, and you use it for teleportation at a non-trivial rate, at a non-zero rate. What we can show is that in these PPT entangled states, the rate is 0. You can't do teleportation with such states. This is the many copy limit Shannon style. You can't do teleportation. Yeah. Yeah.
Entangled states are entangled states that have one positive argument.
When you do the partial transpose. Yeah. So like, let's so this is what I was about to do. Let's define the set of PPT states. This is an annotation that we use, PPT bipartite state. So it's operators such that, well, they're density operators. So these conditions are true. But then furthermore, this is true. So in this set, there are entangled states. By writing this down, I realized another point that I wanted to make. We said we didn't justify that if you're given a description of a density operator and your task is to decide, like a computational task, is to decide is the state separable or entangled. So we said that's an NP hard problem. Deciding whether a state is PPT is an easy problem. Why? All the constraints are semi-definite constraints. So like, you're already told that the state, you just need to check this. It's a linear algebra thing. Right? Right, yeah. It's a simple operation you can do in no more than cubic time in the computer and figure out the answer. So it's often used as some kind of approximation for separable states. And then there's various papers that show, like in high dimensions, maybe the approximation is not so good. But it still can be very useful. And there are other approximations of the set of separable states that is the topic of research. All right. I don't think I have anything else for the day, and we hit the time. So, any other questions? All right. Then enjoy the rest of your week, the weekend. See you Monday. I think the homework is due next Wednesday, right? So if you have questions, come to the office.